Hello, everybody. My name is Shamal Metalia. I'm a principal engineer at Illumina, working in our product development team. I'm here to provide you an update for our latest version of Dragon as part of our webinar, what we call as What's New with Dragon 3.10. We have a lot of slides and materials to cover, so we will run through these slides, and at the end, you will have an opportunity to ask us questions, and then you'll be also having access to this webinar as well as the slides that I'm going to present. So with that, let's get started. Before we get into the details of what are the updates in the latest version of Dragon, I just wanted to start off at the top by asking this question. And this is the question that we ask ourselves internally as we are developing Dragon is, how do you maximize genomic insights? So we want to work on the Dragon platform. We want to maximize the investment that you're doing in terms of our sequencing technology and be able to analyze our data in the most efficient way, but also be able to get the maximum benefits, maximum information that you can derive out of this. So keeping that larger theme in mind, I'm going to cover topics and updates that we have in this version 3.10 to exactly address this high-level question. And you will see, in terms of, what we are doing in terms of improving the platform, in terms of getting more features, in terms of expanding capabilities on how we are trying to exactly answer this specific question. So with that, here are some high-level topics that we will be covering in this presentation. So again, to address that question that I presented in the earlier slide, what we are doing is by maximizing the insights, we are trying to address the data accuracy. So any analysis that you do with the Dragon platform, we want to make sure that you get the most accurate data that we can provide. And with that in mind, we have some improvements specifically to our graph genome, as well as our machine learning accuracy. We are also improving the comprehensiveness of the platform like we normally do by bringing in new pipelines. In this case, we are bringing in the RNA Amplicon pipeline, as well as a targeted caller specifically for GBA, as well as another area that is of focus in our team is to increase scalability of our PopGen and our cohort analysis workflows. So we have a major improvement in this area. And again, this becomes extremely important as we are seeing PopGen initiatives happen around the world, where we are seeing cohort sizes grow. If you think about the UK Biobank, 500,000 samples, the All of Us program that is going to 1 million samples. If you have to analyze those larger cohorts, for example, for GWAS studies, and if you want to bring in new cohorts to an existing cohort, we need something that's scalable, we need something that's efficient, and that's exactly what we're trying to address. So once again, we'll be covering improvements to the platform for accuracy, comprehensiveness, scalability, new tools, updates to existing tools, and so on. Another way in which we look at the work that we do on the Dragon side is breaking it down into specific applications. So there are two, I would say, pillars that we look at. So one is the genetic disease research. So here we are talking about the Germline pipeline, improvements to the accuracy of the pipeline, improving callability or mapping in key genomes or key genes of interest, bringing in targeted callers as we see fit. So these are the things that we'll be covering. And then on the oncology or the cancer research side, we look at tools, that help, address certain applications that were not covered for, in this case, RNA Amplicon. We are looking at ways in which we can make filtering of somatic variants much easier. What can we do for specific, tumor-only samples, looking at specific cancers related to the BRCA gene or the ovarian gene. So these are some of the things that we look at from an application point of view, again, where Dragon can be another useful tool to be used. So let's start with the updates that we have for the genetic disease side of things. There are four main topics that we'll cover here. The first one is we'll share what are the updates we have done in the graph genome. There are some updates that we have made also on the HG38 reference, as some improvements have been recommended from the NIST, or the Genome in a Bottle Consortium. We also have quite a few updates that we have made on our machine learning capability, and moving that machine learning tool from an alpha release to a beta release. And then we'll talk about our targeted caller, which is the GBA caller in this case, which is a new one. And again, this is an important one. It's one of the 113 genes recommended for carrier screening by ACMG. It's related to Parkinson's disease. So again, something that our customers have requested of us, and we now have a caller that can specifically target this gene with a paralog that's associated with it. Okay, so let's first just maybe provide some background and some history on where the improvements have come in terms of the data accuracy. So if you remember, in 2020, the summer of 2020, there was a precision FDA challenge, and the DRAGEN team participated in that challenge, which basically went and looked at difficult to map regions of the genome. And there was a new truth set that came out of it, which was the 4.0 truth set from the NIST. And at that time, if you see the first plot over here, again, just let me explain what the plot shows over here. It's showing the accuracy over all benchmark regions. It is on the y-axis showing you the F1 score, essentially. And then on the x-axis, it is showing you all the entries that were as part of that precision FDA challenge. And the entries were made based on data that was analyzed with either Illumina technology or Oxford Nanopore or PacBio. So coming back to that plot on the left, you can see that in that challenge, DRAGEN version was at 3.7, and we had our first introduction of the graph reference. And you could see where the F score for DRAGEN is. So while it was still the best in class let me bring my pointer here, if I can. Yeah. If you see where DRAGEN was in 3.7, you will notice that while it was still the best in class in terms of the Illumina reads for the F score, it was still not the best if you look at the other sequencing technologies. So in 3.10, we have made some improvements to the graph that has helped to improve that F score. But then the introduction of the machine learning tool has now made it the best in class across all the technologies. So again, a major improvement that was done on the graph and the machine learning side, which has helped to propel the accuracy across all read technologies. On the right side, if you see, it's a similar plot, but instead of the all regions, we are talking specifically of the MHC region. And in the MHC region, you can see that Illumina's entry in that precision FDA challenge in 2020, the F score was lagging in terms of accuracy. So it was, while still better than many of the entries, it was still not the best. So in 3.10, again, we have made improvements specifically in the MHC region for the graph. And that's where you see now the F score improvement. But then when we layer that with the machine learning capabilities, we have helped to improve the F score by removing a lot of the false positives, which is where the machine learning comes in. You can see now it is the best in class. So again, the accuracy of DRAGEN 3.10 across the benchmark regions and in the MHC region, now with this release, at least with the entries that are available to us, we can see that is the best in class across all the read technologies. Another way to also benchmark this improvement is what we did was we took all the genome in a bottle samples. So again, HG001 to HG007. On the left side, you see the accuracy for SNPs. On the right side, you see Indels. And what we are showing is comparison of DRAGEN by itself when you have no graph, and you can see the y-axis, which is essentially showing FP plus FN, how that improves if you turn on the graph capability, and then how it further improves when you turn on the graph plus the machine learning capability. And you can see that the accuracy is holding true across all the samples with known truth that's available to us. So this is a very positive sign where even though you have different ethnicities in this small cohort, the graph and the machine learning, which are more generic, are able to give you the benefits across the board of these cohort samples. Here is a benchmark, again, what we are showing specifically to the MHC region. And you can see that definitely there is a big improvement by using the graph. And in some cases, using the machine learning capability has also further improved the accuracy. We are seeing that in some of the samples, the machine learning is not giving the gains as it was doing for the all benchmark regions in this MHC case. But this is, again, something that is a work in progress. But we can definitely see that the graph improvements have made a huge and significant difference in terms of the errors that we were seeing previously when you didn't have the graph specifically for the MHC region. Again, this capability, there is no additional runtime in terms of the graph improvements we have done, so you can get the benefit of using the graph versus not, and you don't have to run it for much longer than you otherwise would have. In terms of the reference updates, we have identified, or at least the consortiums have identified that there are false positive duplications in HG38, and they have identified 3 genes. These are genes that we think are relevant genes. And hence, as a part of this information, there was a new reference that was released by the Genome in a Bottle Consortium. And what they did in that new reference was they ended up masking these false duplications by ends. What we have done on the DRAGEN side is, because we are now using an alt mask bed file to construct the hash table for DRAGEN, we have just basically updated the bed file to rescue these genes, essentially. So from a DRAGEN user point of view, you just need to adopt a new bed file and just rebuild the hash table versus pulling in a new FASTA file from Genome in a Bottle. Again, so as we said, there are no changes to FASTA that are necessary as long as you take our updated bed file that is part of the 3.10 release. Here is just some benchmarking you can see. So these are the 3 genes that were updated. They were expected to have these variants. For the alt mask file that was in our previous version, you can see that we are identifying false positives as well as false negatives. Once we corrected the bed file with these corrections that were recommended, you can see that we have cleaned up the FP plus FN. So again, you can see that it's fairly easy to update by simply updating the bed file versus having to update the FASTA. I want to talk a little bit about all the updates that we have now made in the machine learning module. The machine learning module is still in beta phase, and I'll explain why. We still have some work to do before we think that it is fully ready or as a commercial version. But again, this has been part of our release since 3.9, and we've gotten excellent feedback from users who have turned this on. So with these additional capabilities, we hope that more users can turn it on and take advantage of it. So what we have done in 3.10 is we have now added support for multi-allelic variant calibration or recalibration. So all these multi-allelic positions will be recalibrated. These were skipped when we released the alpha version in 3.9. There is support now for haploid position recalibration, so specific to the sex chromosomes and then specific to the haploid regions in there. Now we will do recalibration and it matches the diploid positions in those sex chromosomes as well. The machine learning models now also recalibrate in positions where DRAGEN is outputting home reference, so basically 0, 0 genotypes. And we can also use it with forced genotyping now. On top of these additional functionalities that we have put in this release, there is performance improvements. So we are seeing about 5% accuracy improvements on SNPs, so basically improvements to reduce FP plus FN. There is also a smaller improvement that we are seeing on the Indel side. So just overall new features and as well as performance improvements that have happened on the ML model. Just some background in case somebody is new to this module. They have not used it or they're not aware of this capability in 3.9. So it basically applies machine learning techniques to refine the small variant calls and its quality scores. And in 3.10, I listed out all the enhancements that we have made over 3.9. And what essentially the machine learning module does is it runs optionally as part of the small variant calling pipeline for Germline today. It looks at the qual GT and GQ values and it updates them based on the machine learning model. There is a small additional time, a minimal extra processing time, about 5 to 7 minutes. Again, we're calling this as beta because we want to improve on this. We want to try to make this smaller. So hence, we don't think it is ready to call it as a full commercial release, but that's what we are working on. You can use this with whole genomes or whole exomes. And while we are recalibrating some of these scores, the original DRAGEN variant call scores still stay. So in the recalibrated VCF that you get, you will still be able to see both the scores. The way to run it is very straightforward. We have the machine learning model available on our support page. You have to download it and install it on the DRAGEN server. And then on the DRAGEN command line, you can point to that directory where the machine learning model is, and then you simply turn on the machine learning module. Again, another reason to keep this feature still in beta is we are only supporting HG38 today. So we're not supporting 37 and HG19. So again, that's something that we are also looking at to see if we can build support for those references. Just a high-level workflow of what how the machine learning model works or is intended to be in the pipeline. You can see that the workflow is fairly straightforward. As you would have for a Germline pipeline, you start with a FASTQ file or a BAM file. If it's FASTQ, you map align it. If it's a BAM file, you directly call the variant caller. And then you can optionally set on the command line this enable recalibration for machine learning to be true. So this basically runs after the DRAGEN variant caller has run. The input to this model is a pre-trained model that you download from our support side. And then what you get at the output is a recalibrated VCF file. And the recalibration is done over a number of VCF fields. You can also have forced genotyping if you wish that you wanted to call variants at certain positions. And then you can still have access to the original the fields, the VCF fields that the standalone variant caller was putting out. Here is some benchmarking. Again, on the y-axis, we are looking at FP plus FN at the best FN measure point. And here we are basically showing you some color-coded graphs for SNPs as well as indels. And again, the transition is the blue over here is basically a standard pipeline without any machine learning. And then going down all the way to this red plot where we have the graph and the machine learning enabled with 3.10. So you can see that there is an improvement from 3.9 to 3.10 in terms of SNPs. And again, we are seeing a smaller improvement today in terms of indels. But again, overall, you can see that the trend is going down in the right direction as we are enabling additional graph capabilities and improving our machine learning models and also addressing parts of the VCFs that were missed or that were not done as part of 3.9. You can see here the runtime. If you run the Germline caller for a 40x sample with map align, it takes about 20-ish minutes to run. And then when you turn on the ML, it takes about 25 minutes. So again, about a 5-minute additional processing time to get improved accuracy on this pipeline. Finally, on the Germline side, we wanted to introduce the GBA caller. So again, the GBA caller is specifically for Gaucher disease detection. And it also, in addition to the variant calls, it will also generate carrier status information. This caller is only supported today with whole genome data. And just some background on this caller. So it's basically calls GBA variants, which are responsible, which cause autosomal recessive disorder. for Gaucher disease, and the carriers of this disease are at risk for Parkinson's disease. GBA is again one of the recommended genes by ACMG. And the reason we need a targeted caller is because the analysis gets complicated by sequence homology because it has a pseudogene, which is at GBPA1. So the DRAGEN GBA caller is a full-featured caller, as I would call it, is capable of detecting both recombinant and non-recombinant variants, and it differentiates between the reads which have mapped to the GBA gene and its paralog GBPA1. So the way to enable this caller is, again, like if you're familiar with the other targeted callers we have in DRAGEN, it's a single command line option. You just set enable GBA to true. And all references, at least the commonly used references, are all supported in here. And the result or the output of this GBA caller is a output file in TSV format. It tells you the sample name. It tells you whether you are a carrier. So basically, it tells you carrier status, and it tells you, the variant calls, whether it's a recombinant or a non-recombinant variant. So fairly simple to run and targets, this pseudogene. The way it works is, again, very simple. And again, from a user point of view, some of this analysis is transparent because all you have to do is just set the command line to turn it on. But it starts with aligned reads, FASTQ, BAM, CRAM. And then we have internal configuration files specifically for the caller that addresses the GBA and the GBPA1 gene, over which we can compute the copy number. And using that, we can find the non-recombinant variant calls. And for the recombinant variant calls, which have 7 known variants, we look at the exons and the breakpoint detection between these two genes. And the output of the caller, as I said previously, is a TSV file, which includes a list of all the variants that are detected, as well as the carrier status. Here is just some benchmarking that we had done. So this validation was done against 24 samples. Some were clinical, some were 1,000 genome project. Orthogonal validation methods, confirmed that these were positive or true variants. And we have about 24 of those that we looked at. And we can see that the GBA caller in DRAGEN is 100% concordant with this cohort of data that had positive variants for this disease. So again, we feel fairly confident and something that we think I'll be excited to at least give it in the hands of our users to try and give us feedback. Okay, so now moving from the Germline, let's look at the updates that we have on the oncology side. And here we are going to talk about 3 main updates that we have made. So one is the introduction of the RNA Amplicon. So if you're familiar, or if you've been using the DNA Amplicon pipeline, was introduced at a release or 2 releases back. So now we are bringing in support for RNA. And again, this enables gene fusion calling of such samples. We now have a new feature for germline variant filtering. Again, this feature we'll talk a little bit when we get to the slide, but lets you take tumor-only samples and filter germline variants from there. And we are also introducing a new filter, which we're calling as the NTD filter, that is specifically to compensate for deamination oxidation artifacts that come from FFPE samples. Okay, so let's look at the RNA Amplicon pipeline. So again, this pipeline is designed to enable accurate gene fusion calling. Just some background here. So the RNA Amplicon sequencing will perform deep sequencing in targeted regions using custom probes or amplicons, and that is efficiently used to basically validate and screen for gene fusions. So in 3.10, to address such a sequencing approach, we have to have special processing of these RNA-seq reads and then use it with the gene fusion caller to identify these fusions. We have validated the concordance of DRAGEN's RNA Amplicon pipeline versus a pipeline that is available today in BaseSpace that some of you may be using, and we are fully concordant with that pipeline. So we think that we can get some more efficiency, speed with DRAGEN, and something that our users can move to if they wish to. Gene expression can be quantified as well using the target region read counts, which is part of the QC metrics file that is output from this pipeline. To enable this pipeline, you simply set the RNA Amplicon feature to be true. You have to provide an Amplicon bed file so that we know what gene fusions or what genes we are targeting. And then if you want to run the gene fusion caller, you have to set that to true as well. There is an optional command line to provide fusion genes, but these can also be derived directly if you provide the Amplicon bed file. Okay, and again, so as I said, the last one is optional, and the variant calling option is not available today. So again, this is something that we are looking at if we need to provide as a future update to this pipeline, but today there is no variant calling feature on this pipeline. We are only supporting gene fusions. Okay. Just a little bit of the background on what the pipeline is capable of doing. On the right, we just have some example in a more pictorial format on you have two genes. The two genes are captured together, and then they are basically amplified, or you have amplicons across those two genes. In the example here, we are showing the F1P1L1 and the PDG FRA gene. There is a fusion, there is an overlap, and then basically DRAGEN is able to identify this fusion across these overlapped genes. Coming back on the left side, what we're mentioning is, as typical in the Amplicon pipeline, the deduplication of fusion supporting reads is disabled. And this helps us to fully utilize the information in the targeted Amplicon. So, we want to maximize, the information that we can get. So we disable deduplication. A transcript breakpoint that overlaps both genes of the fusion is allowed. So again, you can see that the overlap is over here. And this is allowed as we are showing in this example for these targeted fusions for these genes. There is an ability to have a scoring model, which the user can change and modify. Both genes in a fusion need to be present in this enriched gene list. So this is essentially the gene list that we can derive from the Amplicon bed file. So essentially, you need to make sure that the bed file is properly constructed. We are showing more details in terms of how to create this bed file. It will be available in the user guide. There are a couple of slides as well that would be shared, when you get access to the slide deck that you can refer to in terms of getting more details in terms of how to create that bed file. So, all the information is there. Just in terms of this webinar, we are not covering it, but you can refer to the documentation that comes with it. Moving to the next feature that we have for the oncology side is a population data-based germline tagging feature. So if you have tumor-only samples, and one of the difficulties with there is because you don't have a normal, you are not able to filter out the germline variant. So one way that we are supporting this is by providing ability to bring in a population database. And again, this database can be like I would say 1,000 Genome Project or some of that, where you can pull in this database, and in this example, what we're showing is you can get it from a Nirvana data file, and you just enable the feature that will read this database. The way to configure that database is you could either do it by setting a threshold, and this threshold is essentially the minimum alternative allele count in a database for a variant to be tagged as germline. And we have a default of 40 that we have set, and we'll show some data, some benchmark with that. But you could also set, base it on AF threshold. So it could be the minimum allele frequency for a variant to be defined as germline. So you can set a threshold for that. And then once the database is available and it's enabled as part of the DRAGEN analysis for your tumor-only samples, then we will tag the variant calls as per the database and as per the settings, whether they are germline or not. What you can see here is an example of a whole exome. And on the first plot over here, we show what the sensitivity is, but also the false detection rate. And you can see the false detection rate is extremely high when you don't have this feature. When we turn on this feature, and here on the x-axis, we are showing the various thresholds. As I said, that we have a default of 50 that we are using. You can see that the false detection rate drastically drops. And we are choosing 50 here, at least from this example, is that it gives us a fairly low FDR, but it still keeps the sensitivity extremely high, or as if we didn't do any of those filtering. So you can see that we are getting the benefit of keeping the sensitivity high. We have dropped the FDR, and this is simply done by bringing in a population database which has germline variants. Another feature that we are introducing is what we're referring as a nucleotide error bias correction filter. And again, this filter is specifically targeted for FFPE samples. And the reason or the issue or problems with FFPE samples is there are oxidation and deamination effects that need to be addressed. And this is where this new filter comes in. In the past, or if you are using FFPE samples, you're aware that DRAGEN already has an orientation bias filter. However, we are now saying that you should start using the NTD filter over this orientation bias filter. So while both these filters take account of strand-specific biases, the NTD also accounts for additional biases such as sample-wide elevation of certain SNV types or transitions or transversions. So while it has all the capabilities of the OBF filter or the orientation bias filter, we think it has additional capabilities that can help to lower the number of error counts that otherwise you would see because of the deamination or oxidation effects in the FFPE samples. Again, simple command lines to turn this filter on. And on the right, we are showing two samples that we have analyzed, or two FFPE samples. And again, on the y-axis, we are showing FP plus FN. On the x-axis, we are showing the error counts when you use no filter versus the NTD filter and the OBF filter. And in both cases and both samples, you can see that both those filters help to effectively reduce the error counts. The NTD filter does a little bit better than the OBF in both these samples. And hence, we are saying that moving on with this release, if you have been using FFPE samples, the NTD filter is something that you should consider. Okay, so let's move on to the third big update that we have in this release. And this is specifically for what we call as population genomics or cohort analysis. And let me set some background specifically to why we are addressing this. So one is, of course, we are seeing large population genomics initiatives happening. The cohort sizes are becoming very large. The cohorts, once analyzed, there will be new cohorts that would be done. And how do you address that? How do you combine that? So when we started building out this solution, we had an older ways of doing things on where we would do combining of gVCFs, we would do joint calling of gVCFs and many other things. And we realized that it started to break as those cohort sizes increased. So here are some, I would say, requirements that we set for ourselves when we started to develop this new feature, what we are calling as the Iterative gVCF Genotyper. And again, we are calling this as a beta version because we know we can do better. We have certain optimizations in mind that we can do to improve. But I wanted to just talk over the requirements that we set ourselves when we started to develop this capability. So one is it has to be scalable, aggregate and genotype thousands of samples to millions of gVCFs. You should have the N+1 support, which essentially means that new batches can be added without having to reprocess existing batches. And we should be able to efficiently update the multi-sample VCF of all the batches of cohorts that we have analyzed. It should have all the global statistics. So multi-allelic SNPs, Indels, allele frequencies, sample coverage information. So all of that should be captured into this multi-sample VCF file. We should be able to highly parallelize that. So parallelization across genome shards, or I would say parts of the genome. You should be able to break it down into samples within batches so that you can efficiently analyze them. And of course, address the question of availability. We wanted it to be available in as many places where it's possible. So running it on the DRAGEN server, running it on HPC, running it within our cloud environment, which is ICA, and efficiently scale it over there. So as part of that, here is a high-level table of the availability today of these tools, right? So we've broken it down into the DRAGEN server, HPC, ICA, and then we are showing you what type of analysis you could do for gVCF genotyping. So there is a non-iterative approach which is available today and across all the platforms. But really what we are going for is this iterative approach. And the iterative approach hits all those points that I mentioned in the previous slide. The iterative approach definitely has some limitations on the DRAGEN server, but you can still do it over smaller cohorts, again, because it is limited in terms of its compute and in terms of its memory. Again, this is not something that is accelerated with FPGAs. The way gVCF genotyping works, the way you arrange the entries, it's something that is not suitable for FPGA acceleration. However, when you go to clouds and HPC, you are starting to see the powerful impact of this solution. You can go to several 100,000 samples. This we are saying is not yet available. And again, that's why the feature is in beta. But if you are an ICA user or intend to be an ICA, this will be available very shortly. However, it's available today. If you have an existing HPC, we can deploy it. We have been testing it for several thousands of samples already. Here is just some comparison of the non-iterative gVCF genotyper versus the iterative genotyper. You can see what happened is if you use versions of the gVCF genotyper prior to 3.10, you have 1,000 gVCFs. You bring in another set of 1,000 gVCFs, you have to reanalyze both of them. And if you bring in another batch, so as this cohort starts to grow, this is difficult to scale. You will start to hit limitations with CPUs, memory, time, cost. So all of those factors come into the play and just something that is not scalable at all. With the iterative gVCF, you do your first batch of 1,000 gVCFs, and then you store some intermediate files that could be used later. Now, when you get the next set of 1,000 gVCF files, you create a global consensus file that includes information from both the cohorts. And as you go along this path, you basically are constructing a global census file across the number of cohorts that you are pulling in, and then you are updating the multi-sample VCF files that go with it. So this approach is a scalable approach. It requires less compute as we add more samples. The outputs are smaller. And again, with less compute, you can run things faster. And when you can run things faster on site or in the cloud, it becomes, again, cost effective. So this is the iterative method, and this is something that we're bringing in, and we are available and willing to test with your cohorts as you may have. These are the DRAGEN command line options. So again, this runs off CLI, and I'll show an example of how this runs. But these are the steps that we showed in the block diagram in the previous slide. You aggregate gVCF files from one batch of samples into a cohort file and a census file. As step 2, you aggregate a list of per batch, which means multiple cohorts, into their census file, and then you create a global census file. And in the third step, you generate a multi-sample VCF for one batch of samples from one batch of cohort files, or you can create multiple multi-sample VCF files when you have a global census file that is coming from multiple batches. So again, it's a process that can scale. It's broken down into steps, and then the computational demands, are not as intensive as if you were to run joint genotyping or any of those steps together with a large cohort. Here is an example of how we run this iterative gVCF genotyper on our cloud platform, which is ICA. In the middle, what we have is how you control this process. So there is a population genomics CLI that runs locally on your machine. It lets you control the batches of input data. It lets you control the regions of the genome to parallelize, or what we call as shards. It lets you control the steps, as I showed in the previous slide, the 3 steps that you are running. It lets you manage the instance specs, so the instances in the cloud, and it lets you set the output location of the multi-sample VCF file. In ICA, where you are running DRAGEN analysis to generate your gVCF files, that's where this PubGen CLI will access those gVCF files from. And it will create the cohort and the census files and the related multi-sample files. And again, you can set the batches from the CLI, and then you can aggregate those as new batches come in. From the ICA side, based on the instance specs that we provide, it will bring up one or many instances where it can break down the gVCF files into shards, as we call it over here, and then start utilizing the scalability of the cloud to bring up tens and hundreds of machines as you desire. So again, something that can run fast, can be efficient, and scalable at the same time. I want to talk about some multi-purpose DRAGEN updates as a next section. So there are two features that we'll talk about very quickly here. So one is a downsampling feature, and then the other one is the ORA compression improvements. So just some background on downsampling. So it's something that has been requested from users. As users get different samples, they may either want to align those samples for similar coverages where downsampling can happen, or if you're running some titration testing where you want to figure out, what exactly is the coverage that you might need to get the best accuracy or to get the best F1 score, where you are not oversampling the samples, or whether you're undersampling. So this can help you do some of those testing. The nice thing about this is, in addition to the DRAGEN capabilities from the previous versions, which let you do trimming, FASTQ, you can now just turn on a flag to let you do downsampling. And the entire analysis from FASTQ to map align with all these features enabled runs as a single workflow. So you don't have to go out of DRAGEN to downsample, bring the sample in, and it's easy to now run your end-to-end analysis by turning on these features. This capability exists, for germline samples, RNA workflows. It's seeded, so the pseudo-random sampling will allow for repeatability of the same. The way to enable this is very straightforward. You can turn on the trimming feature. So you say, I want to trim for quality, and you set the quality, to be 20 base pairs. And then you say, okay, this is the filtering I want to do for the length of the reads that I want to include in my downsampling. So you set the value to 100. In this example, we are running RNA samples. So we are saying run RNA, map align, and do quantification. And then we turn on the downsampler and say, I want to downsample up to 15 million reads, but only on reads that have 100 base pairs after you have done the trimming with a quality of 20. So again, very integrated, where you can do all of these steps in a single workflow, and then you can do titration tests if you want to increase or decrease this downsampling rates. Let's quickly go over all the updates that we are going to have on the ORA compression. So again, this is the compression capability in DRAGEN to compress your FASTQ files. We have done optimizations for CPU time and speed and ratio. So we'll talk about that. The capability to go directly from BCL to FASTQ ORA with no gzip steps. Also the capability to do BCL to FASTQ in an interleaved mode. So you can interleave a pair of read1, read2 files. And then also we have capability to make sure that your compression is good, and you can output that and confirm that with an integrity check. So let's talk about the optimization. So in this release, we have a 30 to 35% CPU usage reduction. In addition to that, we also have improved compression ratio. So what we are showing here is the total CPU time to compress a NovaSeq file, which is about 400 million reads at 150 base pair read lengths. The size is about 26 gigabytes. You can see that we have reduced the total runtime in terms of compressing the data. At the same time, what we are showing here is that the compression ratio has also improved. So the file that was 25.8 gigabytes in gzip has been compressed to about a little over 5 gigabytes if you had the 3.9 version, which is in blue. If you go to 3.10, you will see better compression ratio. So not only you're getting faster speeds to compress, you're also getting smaller files than before. In 3.10, we also have an option, again, it's a beta version in this case, where you can do BCL to FASTQ ORA with an interleaved option. So the 3.10 lets you interleave, compressed, lets you compress interleaved files or paired read files directly from BCL. And the output is a single FASTQ ORA file per paired read per sample per lane. So essentially, instead of two files that you have to compare or store, you're essentially storing one interleaved file that has been ORA compressed. That means you're saving less files to manage. And again, you can enable this feature from the sample sheet by setting this option in the sample sheet when you're doing the BCL conversion. What you get out of this is if you were to use 3.9 versus 3.10, the interleaved compressed file is smaller in size. And again, some of the compression is coming from what I mentioned in the earlier slide, that there is a general compression improvement, but also the compression in the interleaved part where you are combining the read1 and read2 files to compress, there is a further improvement. So again, just an overall benefit if you want to have smaller files as well as less files to store when you interleave the read1 and read2 files. DRAGEN ORA also includes an internal integrity check. So this confirms basically that the compressed file is lossless. You can enable this capability by simply setting this command. And what it does as a method, it compares the checksum of the decompressed FASTQ.gz and the decompressed FASTQ.ora. And if the files have equal outputs, we will say the integrity is good. So again, just a quality check to confirm that the files have been correctly compressed and there is no loss. I want to also quickly mention about some additional Germline small variant caller updates that we have made in this release. So the first one that I want to talk about, a VC evidence BAM feature. And essentially what this feature lets you do, and again, this is something that many of our customers have requested, and this lets, especially when DRAGEN is employed in a clinical setting, it lets you get some insight into, the reason or the, when you're trying to investigate a variant call. So this evidence BAM will provide you insight into how the small variant caller sees that read evidence. So if you're running DRAGEN today, you have a BAM file and you have the variant calling file. The BAM file doesn't completely reflect some of the calls that the variant caller is making. And when you go and investigate it, you may see that the evidence may not be complete. And again, this is simply because the DRAGEN variant caller is a haplotype-based caller. It performs local assembly of all reads in the active region. And what this assembly process does is it uses the read bases, including the soft clip bases. And the soft clip bases provide us evidence, especially in Indels. And those are not present in the read cigar. And hence, you cannot see that evidence directly in IGV when you open the BAM file that is coming out of the mapper. So what we do now is we generate a second BAM, or what we are now referring as the evidence BAM. And that BAM will have the exact information that the variant caller is seeing. And hence, you can now investigate that a certain variant call was correctly called or not. So this is, again, very similar to GATK's BAM out feature, if you're familiar with that. But at least it gives you now more visibility into exactly what the variant caller is doing versus previously. Again, you can set this with this single command line, and it will basically generate a new BAM file with the suffix _evidence.bam. Again, just some more information here regarding this feature. So by default, the read alignment is performed only on a subset of the genome. So these reads, these regions which have evidence of Indel variants are, some percentage of the reads that are soft clip. So now with, this evidence BAM, in addition to this new BAM file, we also output a bed file that includes all these regions that have been realigned in the output of the VC evidence BAM. So if you want to even look at, at a high level, instead of opening the evidence BAM in IGV, you can look at all the regions that we have realigned as a result, of using those soft clip reads. And what we are showing here on the right side is you have the original BAM that DRAGEN generates, and then you have an evidence BAM. And in the evidence BAM, you can clearly see that there is an insertion which you would have not otherwise seen if you had opened the original BAM. So again, I think a great feature to investigate certain variant calls, especially indels that you may think that you want to look for evidence. Another feature that has been requested from our users is the ability to have an indel realigned BAM. And again, this is something that we had resisted to put for a while again, and the reason being that we did not see any accuracy gains when you're running the DRAGEN pipeline with this feature. However, there are users who have used this indel realignment BAM files for either historical reasons, because coming from BWGTK where this file is available, or also sometimes they have downstream tools that that require an indel realigned BAM file. And if DRAGEN can generate that, then they can use those downstream tools versus having to create one by themselves. So again, the reason what this indel realignment lets you do is it attempts to correct alignments that are close to indels. This can be run today, integrated in the DRAGEN pipeline or standalone. So, if you have a BAM or CRAM file, you can run it standalone. However, you can turn this feature on. And what we will do is we will have the realigned reads in this BAM file, but we'll also have the original alignment. So, you can have the BAM file with both of them. The workflow is fairly straightforward. You have the mapper and the aligner, and then you have the indel realigner. So if you turn on this option, you turn on this feature, and it creates this indel realigned BAM file with both the alignments. You do sort dedupe and you do variant calling. As I mentioned over here, that there is no major impact on accuracy, but feature requested for certain use cases, which means some customers felt that this is something that they want to use downstream. When we run DRAGEN analysis for accuracy, having or not having this indel realign, BAM file feeding in the variant caller, we did not see any impact in accuracy. I want to quickly then just talk a little bit about updates that are coming on the base space side. So if you're using DRAGEN in the base space environment, there is a new update that will happen to ensure that the RNA Amplicon app is available. So there is a DNA Amplicon app that will be updated so that you can also run RNA fusion calling, read counting, and differential expression analysis. So again, this is just a screenshot of how you can turn it on and off, what targeted amplicons are supported, and then here as an output, you can get a heat map of differentially expressed amplicons. So again, an end-to-end workflow that we have put together, and these apps on base space will be coming out in the upcoming weeks as soon as the 3.10 version is released, and then following that we'll be providing an updated version of these apps. There is another key update that we are making in terms of the base space environment, where now you have the ability to create or generate DRAGEN reports. And what these DRAGEN reports are essentially aggregation of DRAGEN metrics with accompanied visualization. And you could do this either in a multi-sample environment. So if you have a flow cell with many samples, you could run this, but also you could do it on a single sample analysis. And what we are showing here are some screenshots of that sample report. You can see over here as I'm moving my pointer that this lets you see various metrics in a nice report, as well as with visualization. So we are looking at over here the DRAGEN FASTQ related metrics, but you can see mapping, coverage, aneuploidy, variance, zygosity. If you're running HLA, carrier status, for our targeted callers, PGX, so any of these metrics that are being enabled, or features that are being enabled in DRAGEN, we collect the metrics and provide it into a sample report. These are interactive visualizations for FASTQ and alignment results. You can do cross-sample comparisons of QC, mapping, variant calling metrics, and many more. And some of these views are also customizable with tables. Here we are showing reports in terms of a summary report that gets generated, and this is again, it's quick, it's easy. You can do it, as I said, on a single sample. You can aggregate on a per sample basis. So just something that we had been building and putting together, and we'll be rolling out some of these summary reports also as part of our ICA workflows, where customers can generate these reports there as well. So again, I think a feature that can quickly help you glance at how your samples are doing, how you can see any differences that may have happened over the sequencing step for a certain sample versus over a cohort of samples. So I think with that said, this is my last slide. And thank you very much for your time. And I hope these features and these updates that we have made in 3.10 will be useful. Do let us know if you have any questions, and we'll be ready to take any questions now. Or if you have anything later that you want to send us by email, we'll be happy to answer those as well. Thank you.